In this video, I will walk you through some multiple choice questions from past AP exams pertaining to Unit 7. Unit 7 was about 7 theorems that you need to know for AP Calculus. The first one was the first fundamental theorem of calculus, which told us that the end value is equal to the initial value plus the net change in value, which is given to us by the integral of the rate. The second fundamental theorem of calculus told us how to take the derivative of an integral defined function like this one. This is the common case where you just end up replacing the t with the x. So it's sort of like the derivative cancels out the integral and you just get f of x. Then we had the general case of the second fundamental theorem of calculus where we had functions for the limits of integration. So there was a little bit more to it. To take the derivative of this integral defined function, we end up canceling out the integral, and we have function f at v minus f at u. However, you had to then multiply each term by the derivative of the inner function, reminding us a little bit of the chain rule. In addition to the first fundamental theorem of calculus and the second fundamental theorem of calculus, there are 5 other theorems you need to know. I'm going to run through them very quickly. Pay attention to the precondition that you need for each one, which I will show in red. We have the intermediate value theorem, which says that if f is continuous on the closed interval from a to b, and if f at a is less than k, which is less than f at b, then there is a c on AB where f at c is equal to k. By the way, if these theorems don't mean a lot to you as I read them to you right now, don't worry, they will make more sense as we go through the examples. Next we have the extreme value theorem, which just says that if f is continuous on the closed interval from a to b, then f has both an absolute minimum and an absolute maximum on the interval from a to b. The next 2 theorems involve the derivative of a function. So in addition to f being continuous, we need f to also be differentiable. So Rolle's theorem says if f is continuous over the closed interval from a to b and differentiable over the open interval from a to b, and if f at a is equal to f at b, then there is a c on AB where f prime at c is equal to 0. Next we have the mean value theorem, which also involves f prime. Whenever you have f prime, you can bet that f must be not only continuous, but also differentiable. So the mean value theorem says that if f is continuous over the closed interval from a to b, and differentiable on the open interval from a to b, then there is a c on AB where f prime at c is equal to this formula. This is the average rate of change of f. It's sort of an old school slope. Think of it as y minus y over x minus x. Another way of thinking of it is the instantaneous rate of change is equal to the average rate of change, or the slope of the tangent line is equal to the slope of the secant line. Finally, we have another mean value theorem called the mean value theorem for integrals. If we just say mean value theorem, we mean the other one. If we want to refer to this theorem, we have to say the mean value theorem for integrals. This one does not involve the derivative, so it only requires that f is continuous on the closed interval from a to b. If so, then there exists a number c on the interval from a to b, where f at c is equal to this formula. And this is the average value formula, which I like to say as the integral divided by the interval. Problem number 1. If f is continuous on the closed interval from a to b and differentiable on the open interval from a to b, which of the following could be false? Well, the mean value theorem says that if f is continuous and differentiable, there is a c where f prime at c is equal to this average rate of change. In the setup, we are given that f is continuous and differentiable, so yeah, the mean value theorem guarantees that there is a c where f prime at c is equal to this average rate of change formula. Moving on to option B, f prime at c is equal to 0 for some value of c. Well, that reminds me of Rolle's theorem, so let's take a look at that. For Rolle's theorem to apply, f has to be continuous and differentiable, which we are given. But in addition to that, f at a has to equal f at b. Option B does not say anything about f at a equaling f at b, and we are not given that information in the setup. So the preconditions for Rolle's theorem have not been met, so we are not guaranteed that for some value c, f prime at c is equal to 0. This is possibly false. Let's go ahead and go through the other three and see why they are definitely true. The extreme value theorem says that if f is continuous on the closed interval from a to b, then f has both a minimum and a maximum on the closed interval from a to b. We are given that f is continuous on the closed interval from a to b, so that means f definitely has a minimum value on the closed interval from a to b, according to the extreme value theorem. What about option D? F has a maximum. Well, it's the same thing. The extreme value theorem tells us that f has a minimum and a maximum on the closed interval from a to b. We don't need a special theorem for part E. We know that the integral of f of x from a to b is just the area under the curve between a and b. As long as f is continuous, this area, this integral, will exist. Number 2, let f be a function that is differentiable on the open interval from 1 to 10. If f at 2 is equal to negative 5, and if f at 5 is equal to 5, and if f at 9 is equal to negative 5, which of the following must be true? Each of our 5 theorems require that the function is continuous, but here in the setup we are only told that f is differentiable. So I need you to know that if a function is differentiable, it is automatically continuous as well. If this were a free response question, we would have to state this before beginning the problem. Focus on statement number 1. Let's examine and see if this is true. F has at least 2 zeros. Well, f at 2 is equal to negative 5. So I'm just going to put a dot down here to represent negative 5. F at 5 is equal to positive 5. So I'll put a dot up here to represent that. So according to the intermediate value theorem, if f is continuous, then it's going to hit every value between negative 5 and positive 5, including 0. So we are guaranteed to have 1 0 between 2 and 5. Let's go on. So f at 9 is negative 5. So here we have f at 9 will be negative 5. I'll put another dot down here. If f is continuous, then it's going to hit every y value between positive 5 and negative 5 as we travel from 5 to 9. So at some point it's going to hit 0. So the intermediate value theorem guarantees that f will have at least 2 zeros, one between 2 and 5 and another one between 5 and 9. Now let's examine statement number 2. The graph of f has at least one horizontal tangent line. For this, what matters is that f at 2 is equal to negative 5 and f at 9 is also equal to negative 5. Rolle's theorem applies here since f is continuous and differentiable. And Rolle's theorem says that if f at a is equal to f at b, then there is a c where f prime at c is equal to 0, meaning there is a c where f has a horizontal tangent line. In this case, f at 2 is equal to f at 9. So there is some value c on the interval from 2 to 9 where f prime will equal 0. In other words, where there will be a horizontal tangent line. This makes common sense if you just look at the picture and imagine trying to draw a continuous function between the first point and the last point. Well, not only continuous but differentiable, which means that there can't be any corners or, cusps. So there will definitely be some point between 2 and 9 where there will be a horizontal tangent line. As long as f is differentiable, there's no way for it to make a U-turn and come back down without forming a horizontal tangent line at some point. Now let's focus on the third statement. For some c between 2 and 5, f at c is equal to 3. Let's say that 3 is right here. F at 2 is negative 5. F at 5 is 5. If f is continuous, there is no way that we will get from the first point to the second point without hitting a value of 3. This is the intermediate value theorem at work. If f at a is less than k, which is less than f at b, there is some c where f at c is equal to k. In this case, f at 2 is less than 3, which is less than f at 5. So f at c is equal to 3 for some c. Since all three statements must be true, the answer is E. Number 3, the average value of f of x, which equals this, on the closed interval from 0 to 2 is which of these? Make sure you memorize this average value formula. The average value of f of x on the closed interval from a to b is equal to the integral of f from a to b divided by the interval b minus a. Just remember that the average value is always the integral divided by the interval. On this interval, the average value will be given by this expression. 2 minus 0 is just 2, and dividing by 2 is the same thing as multiplying by 1/2. So I'm going to write it this way to save space. Now I'm going to do u substitution. Let's let u equal the stuff under the radical, so x to the third power plus 1. In that case, u prime is going to equal 3x squared. So now we have 1/2 times the integral of x squared times the square root of u. Instead of dx, we write du divided by u prime, which is 3x squared. We notice that we have x squared in the numerator and x squared in the denominator. These will cancel each other out, and the 3 in the denominator is going to end up out in the front as a 1/3. So I will have 1/2 times 1/3 times the integral of the square root of u du. Of course, 1/2 times 1/3 is 1/6, so I think I will go ahead and just do that. Also, notice that I intentionally leave off the limits of integration as I switch over to u. I will bring back the limits of integration when I substitute x back into the expression. The square root of u is the same as u to the 1/2 power, so I can integrate by adding 1 to the exponent. 1/2 plus 1 is 3/2, so I will now have the 3/2 power. Then I divide by the new exponent. Dividing by 3/2 is the same as multiplying by 2/3. Don't forget about the 1/6 that is still out in the front. And normally I would put a plus c right here. However, this is actually a definite integral. Before I bring back my limits of integration, though, I need to bring the expression involving x back into the problem. So instead of u, let's write x to the third power plus 1. And instead of putting plus c, I will now bring back the limits of integration from 0 to 2. This reminds me that I need to find the value at 2 minus the value at 0. 1/6 times 2/3 simplifies to 2/18, which reduces to 1/9. And then on the inside, we have the value at 2 minus the value at 0. 2 to the third power is 8, plus 1 is 9. And of course, 0 to the third power is 0, plus 1 is 1. So now we have this. Remember that when you have a fractional exponent, it is in the form power over root. So this is the square root and the third power. So really, we have this. So we have 1/9 times 27 minus 1, which is 1/9 times 26, which is the same thing as 26 over 9. So that's why the answer is A. Number 4. If f of x is equal to the sine of x divided by 2, then there exists a number c in the open interval from pi over 2 to 3 pi over 2 that satisfies the conclusion of the mean value theorem. Which of the following could be c? The mean value theorem says there is a number c where f prime at c is equal to the average rate of change. On this interval, that means there is a c where f prime at c is equal to f at 3 pi over 2 minus f at pi over 2 divided by 3 pi over 2 minus pi over 2. Given that f of x is equal to sine of x divided by 2, we end up with this expression. 3 pi over 2 divided by 2 is 3 pi over 4, and pi over 2 divided by 2 is pi over 4. So now we have this. Let's evaluate. The sine of 3 pi over 4 is radical 2 over 2. It's in the second quadrant where the sine function is positive. So we have radical 2 over 2. The sine of pi over 4 is also radical 2 over 2. Meanwhile, in the denominator, 3 pi over 2 minus 1 pi over 2 is 2 pi over 2, which is just pi. However, radical 2 over 2 minus radical 2 over 2 is 0. So that means f prime at c is equal to 0 for some value c. To solve this equation for c, we need to find out what f prime of x is. So here's f of x. So what about f prime of x? The derivative of sine is cosine. So I'm going to write cosine of x divided by 2. However, because this is not just x, I need to do the chain rule and multiply by the derivative of the inner function. The derivative of x over 2, this is like 1/2 x. So the derivative is 1/2. This is f prime. That means that f prime at c will be 1/2 times the cosine of c over 2. And where we left off was f prime at c is equal to 0. So let's set this equal to 0 and solve. If we multiply both sides of the equation by 2, that gets rid of the 1/2. And now we have the cosine of c over 2 is equal to 0. Let's solve this equation for c over 2. Where is cosine equal to 0? Between 0 and 2 pi, cosine will equal 0 at pi over 2 and 3 pi over 2. That means that c over 2 will equal pi over 2 or 3 pi over 2. There are other solutions, but this is a good place to start. If I want to solve for c, I'm going to have to multiply both sides of the equation by 2. So I'm going to multiply by 2 here, here, and here. So all of these 2's will cancel each other out, and I end up with c is equal to pi or 3 pi. Let's see if either of these are among the multiple choice options. Kabam! The answer is D. Number 5. What is the derivative from 0 to x of cosine of 2 pi u du? This is just the common case of the second fundamental theorem of calculus. If we have an integral defined function with a constant for the lower limit and x for the upper limit, then the derivative will just be f of x. So for number 5, to take the derivative of this integral defined function, we will just substitute x in for u. This gives us the cosine of 2 pi x. So the answer is D. Ha! Easiest problem yet.